Hey everyone, I just started recording again. I had it off while I was doing some last minute work while I was waiting for you guys to log in. We've still got about 4 minutes before class starts, but if anybody has any questions, by all means, fire away. I think today I got all of our homework due dates set correctly. So for instance, this week, you're now having chapters 8 and 9 that'll be due, but instead of them being due on Sunday like normally, I'm going to make them due on Tuesday, or I already did make them due on Tuesday, which is the 5th, just because we're off on Monday. Don't forget, no classes on Monday due to, I don't know, something called July 4th, which is, a big deal. So anyways, just make sure you get those homeworks done. That's conceptual chapter 8, homework chapter 8, conceptual chapter 9, and homework chapter 9. I'm going to finish off really quickly a couple little issues in chapter 8, and then I'm going to jump into chapter 9. I can get more than enough covered with that, so it shouldn't be a real problem. So, does anyone have any questions while we're waiting?
Yes, I do.
Go ahead.
Oh, about the like opening up the practice test for the recent test. You haven't done it yet?
Yeah, I thought I had. Let me double check real quick while you're here. So let's go to my modules. And this is casting, right?
Yes.
So yes, under your practice test, let's see. It's supposed to be 1 through 6. Where is my practice? I wonder if I put that in the module instead of in the section on practice tests. That sounds like something I would have done. Practice midterm, yes. So it has multiple due dates. It's listed as being available until June 27th, and then 2 students until June. That might be the problem. So I might have meant to hit July and I hit June. So I did set yours, Caston, but I set it to make sure you got it due back in the past on June 7th. Caston, you're supposed to be returning on Monday, is that correct? Or are you back home now?
No, I'm back home on Monday, but I know it's going to be July 4th, so I'll take the test on that Tuesday.
Okay, gotcha. So what I will do is I'm actually making it available until Thursday the 7th.
Okay.
So, and I think I put in that you were going to get it done Tuesday or Wednesday is what I set it for. I think I did the same thing. Actually, Sam Hodge, I did it for a different date because he said he was going to be able to take it, I think, either today or tomorrow. So anyways, it's now up there. I apologize for that. You should have plenty of time now. I made it available to you and Sam until July 7th.
Thank you.
Thank you.
No problem. Was that Sam that had the other question, or was there? It was another male. I think I know it was.
Yeah, it was me, but I had the same question.
Okay, that's cool. Sorry about that. Yeah, I actually did it. I was really prudent. Only I didn't know the difference between JUL and JUN. Evidently, I blame y'all. Really, to be honest with you, it just makes me feel better to blame y'all. I'm kidding, of course. I'm afraid nobody gets my personality from Zoom meetings, but yeah, I'm a bit of a goofball. But as you can see in the background there, I have training pads, so I'm almost house trained. So my wife's working on me. I'm gonna be awesome this time next year. I reverted a little bit during the pandemic. All right, we got some more people coming in. It's now actually time. Does anybody else have any other questions? I've seen the test grades. I know there was some hurt, there was some pain, anguish, and whatnot, and that's somewhat to be expected. Which we got to figure out. Those of you who didn't do, not necessarily even whether you didn't do an A or a B. It's more a matter of did you do what you think you're capable of doing. If you didn't, then we've got to figure out some way, or I say we, I really mean you've got to figure out some way to learn a little more and maybe look up a little less. Obviously, if you're able to get really good grades on the homework, and that mostly looks like what's going on, you might be leaning too much on the solutions that you can find on the internet. a big fraction of physics, it seems weird, but a big fraction of physics is a creativity component. For instance, if you took the equivalent of what we're taking right now, which is more or less mechanics, if you took that in a engineering program, which starts with statics and then dynamics, they have a lot more algorithmic approach. So they'll say, you know, if you've got these forces and you don't know which one's higher, you do this first, then this first, then this first. If that doesn't turn out that way, you do this first. And they got step-by-step problems. We don't want to give you that, because we want you to be able to go out and discover. In other words, try to come up with your own ways. So a lot of the problems I could, in principle, you know, work out in sort of all case scenarios, an algorithm that works, but then you'd have to memorize an algorithm as opposed to just trying to solve a problem. So try to lean a little less on solutions manuals, Chegg, any of that kind of stuff. If you do have to use like an example you found in your book, that's usually good. Like using an example that you found in your book or example that you found on Chegg, if it's not actually the solution to the problem that you're working, it just has some of the similar properties. That's usually a different enough where it's not that much of a problem. But you still want to take and look how they did it, try to get some understanding how they did it, read it pretty thoroughly as best you can, but then close it and try to work it from scratch using what you learned there. So that's what I'd recommend you guys doing. I don't want to tell you to stop making hundreds on your homework grades. I mean, that's fine, but I want you to use the homework grades for really what they are. If at the end of the semester, your homework grades are horrible, but your test grades are great, I might actually look at getting rid of some of your homework grades, specifically because all I care about at the end of the day is your ability to test, specifically on that comprehensive final exam that I usually have. So just try to give that a try. Anybody have any questions after I've gotten off my soapbox now? Okay, so there was two topics we didn't really discuss necessarily in chapter 8, which was on conservation of energy. And one of them was we were going to do a pendulum, and it's just basically a string hanging from a ceiling, hanging from which is a point particle. And I call it a point particle because basically I'm going to use the length of the pendulum, which is from the ceiling to technically the center of mass of whatever you hang on it, what we call the bob. So if I call it a point particle, I can actually draw M as a circle and just write L next to it, and that means it goes from all the way to from the ceiling to the center of the ball. So that's what I'm doing here. And we're going to have this string out at an angle theta 0, as if we know theta 0. We're going to have the mass M as if we know the mass M. And we're going to have the length of the string L, lowercase l, as if we know it. And what we're going to do is try to find some very specific solutions to that. After that, I'm going to introduce you to the concept of power. And I will introduce you to what a kilowatt hour is, as well as what a horsepower is. So that's kind of handy. I don't know if I told you guys this, but just for the record, when you calculate a joule of energy, we're going to go from a joule of energy to watts today. And the difference is 1 watt is a joule every second. And the part that I may or may not have mentioned to you is that I want to let you know that a joule is actually about the amount of energy required to take a nice, juicy, red, delicious apple and lift it from the ground up onto a tabletop. That's roughly a joule of energy. So if you think about running a 100-watt light bulb and how little the power company pays you, try thinking about paying some field workers to actually come in and move, truckloads of apples, and, see how much you have to pay them, even if you're paying them illegally, so that they're, you're not taxing them or anything. You're paying them outright cash or something. You're still going to pay them quite a bit more than you're paying for electricity. So for instance, a 100-watt light bulb is the ability to lift literally 100 red delicious apples to the top of a table every second. So you can imagine the kilowatt hour is on the order of 9, 10, 11, 12 cents a kilowatt hour. And that's 1,000 watts every hour, or 1,000 watts times 3,600, which is 3.6 million joules of energy. So a kilowatt hour is like 9 cents, and you're talking 3.6 million. So it's literally lifting 3.6 million apples up to a tabletop. and they're only charging about 12 cents for that. I don't think you can find workers to work for that cheap. So in some sense, electricity is really cheap. And if you compare it to batteries, electricity is really, really cheap because batteries are way more expensive per kilowatt hour. So anyways, now that I've given you that little spiel, if you will, using my Yiddish, because clearly I have a mastery of the Yiddish language, which I do not. I'm just being funny. I'm going to go ahead and share my screen, and I'm going to share it with my trusty iPad, which is via AirPlay, which is share screen. Nope, I don't want to share it there. Cancel there. I want to do share. Forgot to hit the share button. That was the problem. Now I got my iMac. Okay, so I'm sorry I wrote in cursive. I was just prepping, and that's the quickest way to write. It doesn't look that that good, but anyways, it says calculate the total energy of a pendulum of length L securing a point particle of mass M if the string initially is at an angle theta 0 degrees from the vertical. That's part A. Part B, what is the velocity of the mass as a function of theta? In other words, for any arbitrary theta, not just theta 0. And C, what is the tension as a function of theta? And I also want you to explain the motion. That's generally what the problem is. And you'll notice this is somewhat like a problem that your textbook has in it towards the end of the chapter 8. So first off, I'm starting with the conservation of energy equation I gave you. Again, your book usually uses delta U plus delta K is equal to 0. I showed you how that could become UI plus KI equals UF plus KF. But if you actually want to add some energy loss due to friction, or maybe some work done against a spring, or as you might have noticed in one of the examples in your textbook, it talks about 2 types of potential energy. That's a whole different scenario you can play out. Instead of calling compressing a spring work out or work in, you can actually consider you compressing a spring as increasing another type of potential energy. So the spring has a potential energy given by 1/2 kx squared, where x is the amount of compression or stretch from the equilibrium position. And then you still have, if the spring, for instance, is mounted vertically, you still have a potential energy given by mgh. So in that case, you have 2 different types of potential energy. And that's fine too. That's what I keep trying to tell you about the variableness of these terms in that version that I gave you. That work in might be, for another person, they might call it a U2, meaning a second type of potential energy. Or they might call work out the energy loss due to friction because something's sliding on a frictionful surface. So the main thing is make sure you count all potential energy exchanges and you count them exactly once. Okay. So now that we have this, we're looking at just a pendulum, which is, like what you know of hanging from a clock, for instance, a grandfather clock. We found that as long as the angle stays fairly small, and I'm talking like 30 degrees is actually still like on the order of a few percent or so. But if you keep the angle small, then the actual period of the pendulum is only dependent on the length of the pendulum and gravitational acceleration. So it'll give you a consistent unit or measure of time. So as long as you keep pumping power into it, maybe by winding up a spring mechanism that hits it, gives it a push, hits it, gives it a push, hits it, gives it a push, then the energy will never completely dissipate, and you'll constantly get something that can turn your second hand ahead by 1 click every time it goes by. Or, if you had the exact right length of a pendulum, you'd make it 1 second long for the period, and then it'd be exactly right. So that's what we're dealing with as a pendulum here. In this case, I'm saying I'm not putting any force or work into it. So that's going to be 0. I'm going to say initially we have no kinetic energy because I'm going to drop it from theta equal theta 0. I'm not going to be compressing any springs or doing any work against friction or anything like that. At the end, at any point later, I could have a potential energy or a kinetic energy or both. So for instance, I could consider this length right here or this position right here as having a potential energy that really is a maximum. But in here, I'd have some potential energy and some kinetic energy. Okay. And I'm also ignoring air resistance and friction and stuff like that. So really all I'm going to do is put in what my potential energy is. Now I could in principle call the height of the ball right there, potential energy equals 0. And then what you notice is the potential energy goes up as high as 0. But from there on out, it's always negative or 0. It never actually comes to the positive side. That's fine. You can do that, but I'm not choosing to do it that way. I've decided to set the potential energy equal to 0 at the bottom of the motion. So that's what I'm trying to do here. Okay. Now, what we know is the length of the pendulum's L. So I think you can see that this distance right here, from here to here, is also L. Okay. In other words, to the ceiling to here is also L. And that this distance right here, from here to say here, that distance is in fact, I'll do it like this. That distance is L cosine theta 0. Does that make sense to everyone? That little distance that's on the side of that right triangle that you can see right here, that is essentially L cosine theta. You know, the whole length from ceiling to the bottom of the arc is L. So if you want to know the height, which is this little quantity here, and you want to use U is equal to mgh, then you've got to say, okay, well, H is in fact L minus L cosine theta. So I could say mg times parentheses L minus L cosine theta 0 in this case. And that's a potential energy. Obviously, there's a common factor of L, so I'm going to go ahead and pull that out. And I'll say UI is actually equal to mgl times 1 minus cosine theta 0. So with that in mind, the initial energy, which is, notice that we've canceled out everything except for UI. So that is the total energy. So I can say E total is equal to U initial, which is equal to M times G times L times 1 minus cosine theta 0. Any questions on that? Now might be a good time for me to discuss the actual energy, because I said explain the motion. So what's going to happen here is gravity is actually pulling on this plumb bob. In fact, gravity is pulling on it downward. So it's that force is mg, but there happens to be another force right here that I'll call tension T.
Wait, I have a question.
Yes.
So when you're solving for potential energy, and you say U is equal to mgh, and then U is going to be equal to mg times parentheses L minus L cosine theta 0. So why would H be that small portion instead of being the entire length of L? I don't really get that.
Okay. Well, the neat part about potential energy is, and this is why I showed you earlier, if one of these is true, then all of the 5 expressions I wrote last time are true. Well, one of those expressions was the force is a conservative force, which is what gravity is. But the very last one I wrote was that there exists a scalar potential, which I'm calling U in this case, such that the force, which is the thing we normally measure and use to determine things like acceleration and all that good stuff, is equal to the negative derivative of the potential. So you can add any constant you want whatsoever to that potential energy, and it's still going to work the same. So if you want to assume the height is, let's say, completely L, that would be acceptable as well. In that case, you're saying the ceiling has a potential energy of 0. And then you'd say the H, maybe you put the coordinate system upside down or something like that. But in reality, what you'd be doing is making the potential a superly large negative value when it's at the bottom of the swing, and a slightly smaller negative value when it's at the top of the swing.
Okay, I still don't really understand why we didn't just use L for H.
Okay, well, L, for instance, isn't going to change at all because L is the length
Okay.
of the string, right? So what I'm saying is this total length
Yeah.
from here down to the bottom of the arc, that's L. If I call this part, let's say right here, if I call that part the zero of potential, then my height is really whatever height I have above that. I took the initial height to be the one I showed right here, lowercase h. And what I can see is that dotted red line, vertical line, has a length L, which is the length of the string. But the dotted vertical line that comes to a stop right here, that actually has a length of L cosine theta. So
Okay.
the difference in height is the difference between L and L cosine theta. That's why I came up with the mg times L minus L cosine theta. Does that
Okay.
help you?
Yeah.
Okay. So yeah, it's always arbitrary. For instance, if this was an upstairs window of a lab, you on the ground might look up and say that potential energy that they calling zero is not zero. In fact, that's a good 12 meters off the ground. But they're still completely free to call that potential equal to zero because the only difference is you're adding an mg times 12 meters. But all that really matters is U final versus U initial. So in other words, you're going to do a subtraction. So you're going to have a U final minus U initial. Well, if the U final went up by 12 meters and the U initial went up by 12 meters, when you subtract them, the 12 meters are going to disappear. Does that help a little bit more maybe?
Yeah, thank you.
Okay. All right. So B says, what is the velocity of the mass as a function of time? So I was talking about explaining the motion. So what's happening at this instant in time that I've drawn, it's actually pulled out as far as it's going to go. And we do demonstrations in our physics classrooms like this all the time. We'll take a bowling ball, which, usually weighs at least 8 pounds, some of which weigh, 12, 16 pounds, something like that. And we'll take one and we'll lean our head up against the wall and have it attached to a bolt in the ceiling via a rope or a chain. And I can actually pull that ball back, keeping the tension in the rope nice and taut, and put it right up against my nose like this. And then without giving it any kind of push, I just let it go. And that ball is going to swing all the way across the classroom, reach about the same height it was over here, and come back. And I can confidently stand right there against the wall and know that I'm not going to be hurt, even though that bowling ball, which is like 16 pounds, is barreling at me at a couple miles per hour, is going to come up and at best just touch my nose like it was before. So the only way it could do anything worse than that, like actually harming me, is if it had extra energy, like I had accidentally given a little push by being, not paying attention. If I did that, it could be a bad day. I'd break my nose, right? So we know the maximum energy it's going to have is when the theta is equal to theta zero. As soon as that thing starts to fall, though, the potential energy is way up here and the kinetic energy is zero, but the potential energy will drop by the exact same amount that the kinetic energy goes up, and it'll drop some more and it'll raise some more and it'll drop some more and it'll raise some more. And eventually it'll get to the very bottom where we call potential energy equal to zero. At that point, the potential energy is zero, but the kinetic energy is exactly equal to mg L times 1 minus cosine theta. Numerically, obviously the kinetic energy is 1/2 mv squared, but that's what's going on. So that's what the motion is. The motion is a sloshing back and forth. You can imagine a Ziploc bag with two baffles. So you have a semi-osmotic membrane between one half of the bag and the other half of the bag, so that air can sort of flow between them, but it doesn't really do it unless you apply a greater force or a pressure or something. So initially, when the pendulum's all the way up at theta zero, the K baffle is completely empty, but the U baffle is completely full. As the pendulum starts to fall, you start to squeeze the U baffle, squeeze, and exactly as much as the U baffle shrinks, the K baffle will go up. And that's what's going on. It's sloshing back and forth between those forms of energy. And this happens a lot. This is as long as the angle is small, this is equivalent to what we call simple harmonic motion, which we'll study in chapters 14 and 15. But in reality, it happens a lot of other places too with actual springs. And with other things. It turns out, for instance, that physicists study springs, not because springs are awesome or because we're nerds and only like springs, but because if you take any potential energy function that actually means anything, you can do a Taylor series expansion on it. The Taylor series expansion is like some number times the zero derivative of the function evaluated at, say, x equals 0. That's actually the Maclaurin series. And then the next term is some constant, a new constant, by the way, times the first derivative evaluated at x equals 0. And then the third term is a new constant still times the second derivative of, or excuse me, times the second derivative evaluated at 0 times x squared, whereas it was x to the 0, x to the 1, and then x to the 2. You can expand every function that way. And it turns out if you're near equilibrium, like you're talking about the potential of an atom between two other atoms, that middle atom that you're focused on is usually going to find itself in equilibrium where it's nice and comfortable. That means the potential energy is at a minimum, right? Does anybody recall from calculus, if you say that the function u has a minimum at x equals 3, say, can you tell me anything about the derivative at x equals 3?
0.
Is 0. That's because the minimum has a horizontal slope, right? So now we've got a function by that Taylor series or Maclaurin series expansion. The function is going to be a constant, which you can add at any time. Like I told you before, you can add any constant to the potential energy you want. So we can just pretend that constant is going to be 0, or it's just the quantity that we added. Then the second term is going to be some number times the first derivative times x to the 1 power. But if we're near the equilibrium, the first derivative is 0. So that term is going to completely disappear. And then lo and behold, the very next term is some constant times the second derivative times x squared. And guess what? The potential energy for a spring is 1/2 kx squared. So it's just a constant times x squared. So that's why we study the spring, because so many things near equilibrium are going to behave like a spring. Okay, we'll get into more of that later on when chapters 14 and 15, but I just wanted to let you know that's why we study a pendulum as if it's simple harmonic motion, and then we do springs and all that sort of stuff. So now that I've explained the motion, I'm going to talk about what's the final velocity, or what's the velocity as a function of the motion. So I know that the energy, the left-hand side, is just mgl times 1 minus cosine theta 0. That's a constant of the motion. That is, in fact, the total energy. But on the other side, it's going to be mgl times 1 minus cosine theta for whatever theta it is. Obviously, theta can't be any larger than theta 0, but that's the potential energy at any time later. And also at any time later, you've got the kinetic energy will be 1/2 mv squared. Obviously, you can see that the constant factor of m can be divided through with no loss of generality. So now all I got to do is solve this for v. I'm going to first off, now that I've divided by m, I'm also going to multiply through by 2, and I'll get 2gl times 1 minus cosine theta 0. Now I'm going to bring the 1 minus cosine theta over to the other side. When I bring it to the other side, the 1 is going to be a negative. And then the cosine theta is going to be the negative of negative cosine theta. So it'll be plus cosine theta. And then all I have left is v squared. So v is going to be equal to the square root. And you could say plus or minus. I'm just going to ignore that part right now. But it's going to be v equals 2gl. Notice the ones canceled out, and I get cosine theta minus cosine theta 0. So that is the velocity
I have
for
another
any
question.
given angle theta. Yes.
So you crossed out m because there's m on both sides, and then you just subtracted gl times 1 minus cosine theta.
Yeah, I pulled it over to the other side, so it'd be mgl parentheses 1 minus cosine theta 0 minus, or excuse me, I got rid of the M, minus GL times parentheses 1 minus cosine close parentheses. That minus has to be distributed. That's why I got a -1 and a positive cosine theta. Does that make sense?
I'm just confused because I feel like GL times 1 minus cosine theta to subtract that from one side, why wouldn't that just be 0?
Yes, the one term did become 0. That's why you don't see a 1 inside the parentheses anymore. You just see M 2 GL.
Okay.
Let me show it to you a little clearer. We'd have GL times 1 minus cosine theta 0 minus GL times 1 minus cosine theta. That would be on the left hand side. You can distribute that GL and you see the GL times 1, and then there's a negative GL times 1. That's why I got this and this canceling out. You see a negative cosine theta 0. That's why that's in there. And you see negative of a negative, and that's why that's in there. You're tracking now?
I'm still getting 0, but
Well, remember, one of the thetas is subscripted 0.
yeah, okay, and they're not both 0.
Exactly. It's theta 0 is the biggest the angle can be. Theta can be anything up to and including theta 0. And technically, it's only going to be theta 0 that very first time. It'll be infinitesimally smaller than theta 0 when it gets back.
Okay, thank you.
Okay. All right. Now, the last part we want to do is find what is the tension as a function of theta. So I'm going to draw a free body diagram to help us with this one. And the free body diagram will look like this. I have this rope. It's got a length, well, excuse me. It's got a length L. I have this mass M that for some reason became a square instead of a circle. Now it's a circle. Okay. I have a force acting on it, mg, and I have a tension acting on it, and that's going to be T. And now I'll go back to just plain writing. So this one's mg. And what you can say is that this angle right here is theta, and the summation of the forces in the y direction equals mass times acceleration in the y direction gives us, in fact, well, it's not that helpful there, but we also have to have the summation forces in the x direction equals mass times acceleration in the x direction. That again is not that helpful, but if we think about this for a second, we can sort of say, wait a second, let's call this my x-axis, and let's call this my y-axis, okay? And this is my x. And then you realize, oh, wait a second, the acceleration has to be in the y direction, right? So in this case, I'm going to get, I can break this part up here. This is theta that I've drawn here, right? Now, if I go over here, this angle is 90 minus theta. And that's the vertical angle with this. So that's 90 minus theta, which means this is also theta. So this side right here has got to be mg cosine theta. And this side down here has got to be mg sine theta.
I have another question.
Yes.
Couldn't you just tilt this on the side to make x parallel to the x graph so you wouldn't have to do the extra drawing? Like
Yeah, but I needed to basically make it at an arbitrary angle. And that if I did it up and down like that, you might get the impression that I'm calculating it just for the bottom. So I wanted to make sure you knew I'm going to calculate it for any angle theta. Does that make
Okay.
any sense?
Yeah.
Okay. So yeah, you're absolutely right. That would be sort of a smarter way to attack it. I didn't want to lead you to the mistake that we're calculating the tension when it's only theta equals 0. So now if I take the summation of forces in the y direction, I can see that the forces acting are in that case T, which actually acts in the vertical direction, minus mg cosine theta. That's the only two forces acting in the y direction, but the y direction has an acceleration, and that acceleration has to be mv squared over L. Okay. That part right there, which I'll call equation 1, allows me to solve for the tension. The tension is in fact going to be equal to mg cosine theta, because when it comes over to the other side, it'll be positive, plus m over L. Now v squared, we've already worked out. We found out that v squared would be 2 times g times L times cosine theta minus cosine theta 0. So I'm going to make this into a square bracket and that into a square bracket. You can see now that the L's will cancel out like that. And I'm going to get mg cosine theta plus 2mg cosine theta minus 2mg cosine theta 0, or finally the tension as a function of theta would be mg times 3 cosine theta minus 2 cosine theta 0. Any questions on that? All right, so that was the last quote unquote problem I wanted to work with. The last thing I want to do with regards to chapter 8 is I want to find power. On average, power is equal to the work done divided by the time taken. Anybody have a guess what we're going to do if we want to find the instantaneous power as opposed to the average power?
Are we gonna plug in number at a specific point?
No, not in this one. I mean, we're going to use some numbers to talk about units, but we're not going to do a numerical example here. You can go back and do numerical examples with the values that I just derived on that previous problem, though. But actually, I did it, I think, almost identical to what your book did. So anybody have a guess how we're going to change that average power is equal to work divided by delta T? Anybody have an idea what we're going to do to make that instantaneous power?
Are we gonna use energy?
You can replace work with energy because work basically is something that gives something energy. But can you think of anything we did in the past to convert an average to an instantaneous?
We took a limit
Exactly. Take the limit as
yeah.
delta T approaches 0.
to
And
zero.
that's called a derivative with respect to time.
Oh, right. That exists.
Right. Okay. So that's what power is. And just to give you an idea, does anybody know of a unit of power? Maybe the unit of power that your car manufacturer would tell you about your car?
Is it horsepower?
Yep, it literally is. And it literally means horsepower, meaning you can take, 100 horses and let them pull a plow, compute what that force is or measure what that force is, and then measure the distance they travel in say a single day or 6 hours or whatever. and you take and multiply that force times that length, that distance traveled, and then divide that by the number of hours. And lo and behold, you'll get that 1 watt, or excuse me, 1 horsepower. 1 horsepower is equal to 746 watts. And a watt is a joule per second. So the other unit of power is 1 joule per second, which equals 1 watt. Okay. So with that in mind, we happen to know that dW is equal to F dot dl. So with that in mind, you might think that dW over dt, which is actually power, is going to equal, say, F dotted with dl over dt. Anybody have an idea what dl over dt would be?
Speed.
There you go, speed. And since it's actually a vector quantity, it's going to be velocity. So there's another expression you can use. I will tell you in this chapter, basically all the problems that you're going to do with power, just about all of them are almost always, calculate the amount of work done or the amount of energy absorbed or something in some interval, and then divide it by the amount of time taken, and that's the power. Or they'll give you the power and then say, well, how long is this going to take? Or they'll give you the power and tell you it takes a certain amount of time, and they're going to ask how much work or energy it is. So you can see the vast majority of the stuff is really trivial. But if they give you something like the thrust of a boat propeller is 10,000 newtons and the power is 842 million horsepower, then you're going to convert that to joules and then realize that F dot V is just F times V when you're talking about force of a propeller and the velocity of the boat, and you can calculate what the velocity of the boat is. So that's really the scenario here. One thing I'd also like to mention is, does anybody know what your power company charges you for? Like when you get a bill, you get a certain number of dollars that you have to pay, and that's based on like 12 cents per, I said it earlier, kilowatt hour. Do you know if you're buying energy or power there? I mean, it's called the power company. You'd think you're buying power, right? So what do you think it is?
Isn't it energy?
Yes, it is actually energy. And 1 kilowatt hour should technically be written like that. That's a kilowatt times an hour. Now, you know that a kilowatt is 1,000 watts. And in fact, you know that 1 hour is 3,600. Whoa, I don't know why I wrote a 0 there. I mean, a 1 there. And 1 hour is 3,600 seconds. So you can see that a kilowatt hour, remember a watt is a joule per second. Whoa, why did I go to erase? I don't understand this. Oh, I know why my pinky got up in there. A watt is defined to be 1 joule per second. So if I multiply a joule per second times a second, I actually get joules, and that's 3.6 times 10 to the 6 joules. So a kilowatt hour is, like I said earlier, 3.6 million joules. So again, imagine paying 12, 13, 15 cents for someone to lift 3.6 million apples, a height of roughly a meter. All right, that finishes chapter 8 in its entirety. Anyone have any questions? All right, looks like we're doing pretty good then. So what I'm going to do next is I am going to go into, we already started into chapter on momentum. I even hinted some things about what Newton actually said about his second law, all that good stuff. But I'm going to solve some problems, and I'm going to actually work out some specific formulas and some specific problems, and even get you some nice equations that you can use to solve momentum problems. So it turns out that Newton in his Principia, for starters, they didn't have vectors then. Vectors were an invention of the 30s through 60s roughly. So a lot of the wording of the Principia is about Newton talking about not only the magnitude of quantities, but the direction in which they were going. Because, you know, we hadn't invented vectors yet, so you just couldn't say a vector quantity. So what Newton said was the summation of the forces is equal to not MA, but in fact it's dP dt, where P is defined, at least classically, to be mass times velocity. Okay, now you can see from that, this is actually the more general expression, this dP dt, okay? Because of that, you can say the net force acting on a system would be dm dt times v plus m dv dt. So this term right here is the MA we're used to. This term right here is actually very important. That's the part that it plays a large part in rocket propulsion. So when a rocket takes off, it's got to bring all of the little articles of clothing or whatever, like I talked to you about being on a frozen lake. If you're on a center of a perfectly smooth frozen lake, that means it has zero friction. There's really no way for you to walk, because if you try to walk, you've got to push down and backwards on the ground, or on the ice in this case. And the ice will definitely push back up. That's not a problem. But because it's frictionless, the ice cannot push forward, according to Newton's third law, is what it would try to do. But because it has no friction force, it can't push you forward. Ergo, your falling forward is just going to continue you falling as opposed to you actually moving. So you can't actually move off the center of a frozen lake if it really is truly frictionless. But what you could do is say, take off your toboggan, hold it about the height of your belly button, because that's roughly where the center of mass of most people are, and do a stomach pass, the opposite direction you want to go. Now, that's a toboggan, so it doesn't weigh very much. So just like hitting a fly, you can't apply much force to it. But any force greater than zero is a force greater than zero. And according to Newton's third law, if you apply a force of 0.02 newtons to a toboggan, that toboggan is going to apply exactly the same force, 0.02 newtons, to you, but in the opposite direction. And that's your propulsion. So you'll not have an acceleration of, say, 0.00001 meters per second every second. But if you're willing to wait long enough, you'll eventually get to the other side of the pond. Obviously, you're going to freak out a little bit. So then you're going to start pulling off other, items of clothing, maybe shoes, shirts, gloves, wallets, belts, all sorts of stuff, and just start throwing them the opposite direction. Well, in outer space, you have to take all that crap with you, right? It can't just have a spring that presses against a nearby planet and shoot you off of it. No, it's got to throw a bunch of projectiles in the opposite direction it wants to go. So the reason that you see, for instance, old videos of the space shuttle taking off, where they have these huge tanks under them that are sometimes 2 and 3 times the volume of the space shuttle, is because it's got to carry all that fuel. So that DMDT is really the loss of fuel happening. And we're going to skip that section in this chapter, but I just want to let you know, jet propulsion really uses that DMDT a lot. Now, the other thing I'm going to talk about this is, if the net force is equal to 0, then dP dt, and we talked about this earlier, is also equal to 0. So that means P equals a constant. Now, you could talk about P as if it's the momentum, or the momentum of a particular object, like the mass times velocity of a car, but it's often way smarter to use a system. So for instance, you could talk about the momentum of a 2-car system. For instance, a car headed eastbound on Dam Neck Road with a car headed northward on Princess Anne Road. If you treat them both as part of the system, then the force one of the cars puts on the other, or vice versa, isn't part of the summation of the forces. So you don't have to worry about that at all. The only forces that are acting on your system now are gravity, which is being canceled out by the normal force of the road, and then the friction force acting between the tires and the road, which you can imagine if the cars are going 50, 60 miles per hour, that friction force is going to be pretty small. And if you also take into consideration that a lot of car wrecks nowadays happen because people are texting while driving, they never even have an instant of thought to try to decide to actually hit the brakes. So they're not even going to skid. They're just going to go into it full force. And that's why wrecks can get a lot more deadly nowadays. Same thing happens if someone passes out at the wheel from either a medical condition or drinking or drugs or whatever. So a lot of collisions, it's completely true to say momentum is conserved. And that's what we mean when we say P equals a constant. Does that make sense to everyone? Okay, so P equals a constant is a particularly interesting problem. What I'm going to start off with is Andy Roddick's serve. I'm pretty sure that's who the picture was of in your book. And they said basically his final velocity of his tennis ball was about 55 meters per second. He said the amount of time the string was in contact with the actual ball was about 4.0 milliseconds. And the initial velocity, of course, would be about 0. The mass of the ball is 0.60 kilograms. And in fact, the American Tennis Federation or the International Tennis Association, they have very strict rules. If Wilson wants to manufacture, or Penn or whoever wants to manufacture tennis balls, then their tennis balls have to meet certain criteria, one of which is, I think the mass has to be between 0.585 and 0.618 or something like that kilograms. Also, they have to have a certain amount of springiness versus stiffness. So they've got other parameters they do as well. But the main thing is you could actually look up what those balls weigh. Obviously, if you're getting ready to hit a golf ball with a baseball bat, you're going to have a lot harder problem dealing with that. But you can still look up the mass of a golf ball and do that. And by the way, don't do that. I've done that before when I had a hugely open field. And if you hit a golf ball with with a baseball bat, especially a metal one, that sucker's going to go off really fast and could really kill somebody. So I don't recommend doing that. But what we're going to do now is try to calculate the average force that Andy Roddick applies to a serve. Okay. Now, be advised, this 55 meters per second, your book tells you that's 120 miles per hour, and that's about right. But your book's a little dated. The new edition's now out. This one, I think, is maybe 8 years old. 120 miles per hour was not even impressive when Pete Sampras was playing tennis. Pete Sampras was hitting 130, 138, 135. Rafael Nadal occasionally will hit, 150, 151, 152. Serena and Venus Williams, even though Serena lost yesterday in Wimbledon, they consistently hit in the 120s. And often in the 130s. So the game has actually progressed quite a bit since then. But either way, we'll still go ahead and calculate it. What we know is that the summation of the forces on average, especially if we're dealing with one dimension, is just delta P over delta T. Okay, that's the average force. And that's okay. We can use that because, it's going to be a small period of time. It's probably pretty close to the derivative anyways. So if we want to calculate that average, all we got to do is say P final minus P initial, because that's what delta means, over delta T. Well, P final is 0.60 kilograms times 55 meters per second minus 0, because the initial momentum is 0, not because the mass is 0, but because the velocity is 0. Now, you also, of course, know that when you hit a tennis ball like Andy Roddick or somebody does, they throw the ball upward. It's probably moving a little bit upward. It's also probably moving a little bit outward towards the other player. And in fact, Andy Roddick's serve is going to involve so much momentum of his arm, it's going to lift his whole body off of the ground and into the court area. But he's still going to have to hit the racket pointing somewhat upward. And that's going to last for about 4.0 times 10 to the negative third seconds. Okay. If we are to trust your book on this issue, I think it comes out to 800 newtons. So that answers about 800 newtons. If you take a 60 kilogram person, then mg for a 60 kilogram person is equal to 60 kilograms times 9.80 meters per second every second. You can see that that's going to give you, I did not bring my calculator. That was not smart, Mr. Younger. Thank you. Okay, so 60, enter 9.8, multiply, and that gives me about 588 newtons. Now I'm starting to wonder if I misremembered the number. Maybe the number, well, now that I have my calculator out, let's do it. 0.6. Okay, it just does not want to hit the decimal today. 0.6, enter, 55, multiply, 4 e to the -3, divide by, whoa, it was 8,000. What the boots it? Did y'all get an entirely different number than 800? I got 8,000 newtons this time. That seems a little bit more reasonable to me. So let me erase that. Anybody back up my calculations?
Seemed right.
Okay, so it's 8,250 newtons is roughly what we got. Your book claimed that was about as much force as a 60 kilogram person weighs. I'm going to call poo-poo on that. And I'm sorry to use such harsh language with you young people. I apologize in advance for that. So let's instead try to get an estimate of what 8,000 newtons is. So let's say 8,000 newtons is equal to m times g, so that the mass of that fat somebody might be 8,000 newtons divided by 9.80 meters per second every second. Now I can do that math because I got super skills with my calculator. 8,000. Notice I'm just rounding to 1 sig fig. That's why I used 8,000. 9.8. I'm going to divide that into the 8,000. And I'm going to get 816 kilograms. So that's kind of heavy. And in fact, if you multiply it by 2.2, that's almost a ton. So he's hitting a ton. I don't know where I got my numbers before earlier. I don't see any mistakes here, unless the tennis ball was 0.06. Maybe that was it. Let's see that. I'm trying to look up in the book right quick just to make sure. That might be what happened. I might have, the tennis ball might actually weigh 0.06 instead of 0.60. Well, luckily I'm just way back at page 8,472. So this won't take but for an hour. I'm thinking that's what happened. That makes much more sense to 60 kilogram ball instead of a 600 gram ball. I really don't think it's a 600 kilogram ball. And let's see. So we're going to change it to Andy Roddick's shot putting, I guess. Oh, that's what it was. It was off by a factor of 10. Okay, that makes a lot more sense. Okay, so I'm going to write on here because all this is valid with what I said. It's just I used a fat ball, and obviously he's not going to hit a fat ball at 120 miles per hour. So this is done using m equals 0.60 kilograms, but ball actually weighs 0.060 kilograms, which implies F average is equal to about 800 newtons. which means, okay, if I take 800 and divide it by 9.8, that'll be a much more useful scenario. 800, sorry about that, everybody. 9.8, God, that sucks. Is about 81 newtons. Actually, it's more like 82 newtons. Or excuse me, 82 kilograms. Which is multiplying that by 2.2. Because 1 kilogram is about 2.2 pounds. So that's about a 180-pound person. Okay, so I've corrected it now, at least on our notes. Everything else was okay. I'm just going to say, put this here. Just remind you, hey, look at that. Mr. Younger's a goober. He made the terrible mistake of saying a ball weighed 0.6 or 600 grams. So anyways, any questions on that? Other than why are you so dumb, Mr. Younger? I prefer you refrain from asking that at this point. All right, so there's a momentum problem, a very typical momentum problem. They can tell you what is the change in momentum, and you tell them how much, or if they tell you how much time it takes, you can tell them what the average force is. Your book even does an example where it talks about water coming out of a water hose. If you, for instance, want to consider the force that can come out of a pressure washer, I will tell you that when my wife that I have, my new wife, when she first met my mother, it was after my mother was pressure washing something for like a side job, and she laid a pressure washer on her big toe and like literally broke her big toe and had to have stitches and stuff like that. So a pressure washer can do some serious damage. But if you want to think about it that way, you can think about something along the lines of force is equal to delta P delta T. Okay, and that would be the average force, the average net force, if you will. But delta P is actually delta M V over delta T. So you could say delta M is rho times V, where this is the actual volume, and then this is the velocity over delta T. So it could be the density of the water times the number of gallons per minute times the velocity. Well, it turns out that delta V over delta T, which again, I would say is measured in, say, gallons per minute. That's a typical unit. In fact, for instance, I was doing wastewater engineering and potable water engineering once, and one of the stipulations you have by code is that if you're using a water tower or any other kind of water source, and you're going over an entire what they call planned urban development, a PUD, then you're required by law or by code to make sure that you can deliver 500 gallons per minute at the farthest, most distant fire extinguisher, or excuse me, fire, you know what I'm talking about, fire hydrant. So basically that's a typical measure. But here's the neat thing, the gallons per minute is really, like I said, a delta volume. Well, let's not do that. It's the change in volume per change in time, but the volume is actually area times the length over delta T. So if you're talking about a water hose like this with a cross-sectional area A, and this is the length L, then you can see the volume per unit time is actually the area times the velocity. So now we have mass times velocity, which in fact gives us roughly the average force, or you could use the air, the pressure pressure is equal force divided by area. That's really the definition of pressure. I could say that force right here is the same as this force. And I'm going to say that is the density of water times the area times the velocity times the velocity again, because we already had velocity, and all that would be over delta T. So, and of course, all that has to be divided by A because we're calculating pressure. So we'd end up getting the pressure is equal to the density, H2O, times the volume squared, excuse me, times the velocity squared. Okay. So that's another way of looking at it. You could actually use that then to calculate the average, or excuse me, to calculate the pressure applied by a given water hose or something like that. If you just wanted the force, then of course, you're just going to take the pressure and multiply it by the area to get the force back. So that's fine as well. Now, I'll tell you that in reality, experimentally, it comes up to 1/2 rho V squared is what the pressure is. That back of the envelope calculation that I just did misses the 1/2. But if you cover fluid dynamics, you'll get that. So that's another thing you can do with conservation of momentum, or just the understanding of Newton's second law as being the average force equals the change in momentum divided by change in time. Your book does do an example like that. I just wanted to sort of outline it and give you some different ideas of what to think about. The only expressions I used are ones I expected you already knew. That is the density of a fluid, of anything for that matter, is equal to the mass divided by the volume. And I'm trying to use that V specially there, so you'll understand that that's different than the velocity. Okay. Oh, and I also use the definition of pressure, which is defined to be force divided by area. And you can see already we're having problems with the nature of our alphabet. I've got P being used as pressure. I've got P being used as power. I've got rho, which looks like a P, being used as density. I've got capital V being used as volume, and then V being used as velocity too. So that's why we actually have to go into the Greek alphabet. Now, I've done that. Your car does that, or your book does that. In example 9.2, it says washing a car, the momentum change in force. So you can actually use some of the ideas I just gave you to come up with that. Now, the next part I want to do is actually consider collisions. So I'm going to say chapter 9 continued. And what we're going to do is we're going to imagine basically collisions. Specifically, we're going to choose a collision in one dimension as the low-hanging fruit. But first off, I'm going to introduce you to the general expression of collisions. So momentum is conserved. What does that mean? Well, you could have, for instance, a ball A that has a mass A moving with a velocity VA towards a ball of mass MB moving towards it with a velocity VB. Sometime later, they're going to collide, A and B, and then maybe A will fly off this way with a velocity VA prime, and B might fly off this way with a velocity VB prime. Okay, so that's an actual reality. That's something that could happen. And in fact, conservation of momentum would tell us that MAVA vector plus MBVB vector is equal to MAVA prime vector plus MBVB prime vector. Okay, now what does that mean? In general, that could mean 2 or 3 dimensions. I'm going to write out 2 because I can, and it's a little bit easier than going ahead and writing a third. So what that means is MAVA sub X. So I'm trying to subscript the VA with an X plus MB VB sub X is equal to MA VA prime sub X plus MB VB prime sub X. And then you get the same thing for the Y, be MA VAY plus MB VBY is equal to MAVAY prime plus MB VB prime Y. If it's a three-dimensional problem, you could in principle have a third equation. But if the equation was also, or if the collision is elastic too, then you have 1/2 MAVA squared plus 1/2 MBVB squared is equal to 1/2 MAVA prime squared plus 1/2 MBVB prime squared. So at most you can have, if you have a non-elastic collision, or if they just didn't tell you it was elastic or not, the most unknowns you can have is 2, because there's 2 equations. However, if they tell you that it's also an elastic collision, then you can actually have 3 unknowns. So those are our equations that we can use, and they all come from the assumption that the net force is 0. So that's the only assumption with regards to conservation of momentum, is net force equals 0. Okay. This one is kinetic energy conserved, which is the definition of an elastic elastic collision. So now let's look at a typical problem. I'm going to do a skim border. Okay, y'all probably know what a skim board is. It's usually a little short, fat, surfboard shaped piece of plywood with a little bow in it. So it's got a little upward bow at the front, at the tip. It's usually laminated pretty nicely so that it, or not laminated, but got polyurethane on it, so it's nice and smooth. The top side, they usually make it a little gritty and put some surf wax on it or something to make it a little bit more tacky. You wait for a wave to come to the beach. The wave will then wash a little bit of thin skim of water up the incline of the beach. And then your job is either during that up motion or during that down motion, you give the skim board a little toss and it slides smoothly, nearly frictionlessly with that. And then you run, jump on it, hopefully matching up the speed, but then you're actually stuck on it. And that is the very definition of a perfectly inelastic collision. When 2 objects collide and end up sticking together, that's called a perfectly inelastic collision. And the reason that it's called that, so y'all can rewind this later and check in case you forget, but in a what we call a center of mass frame, what you do is you try to create a system where the total momentum is 0. So if you had, for instance, an electron moving at a stationary electron, and the moving electron was moving at 1,000 meters per second, what you can do is switch to a reference frame in which that original electron's moving to the right at 500 meters per second, and the other electrons moving to the left at 500 meters per second, so that mass times velocity in one case is the negative of the other case. So the total momentum before the collision is 0. If that's the case, then what's going to happen is the 2 electrons will collide in that reference frame and come to a complete stop. And since it comes to a complete stop, the kinetic energy is now 0. Okay, so they call that a perfectly inelastic collision, because in it, the total kinetic energy is lost. So that's what all that's about. So a perfectly inelastic collision is whenever the 2 objects stick together. So let's look at a skim border, and we're going to say the skim board has a mass of 3.00 kilograms. Let's say I've given it a push of V equals 2.00 meters per second. And then I am going to jump on it. I'm going to jump on it with my mass of 100 kilograms. And I'm going to be moving with a velocity me of 1.50 meters per second. Okay. This is not an elastic collision. What I want to know is what is the velocity of me plus the skimboard afterwards. So the initial momentum P of the system is 3.00 kilograms times 2.00 meters per second plus 100 kilograms times 1.50 meters per second. You can see the units are going to be kilograms meters per second. You could also call that a Newton second if you wanted, but nobody does that. Everybody calls it kilogram meter per second. So this is 150 plus 6, that's 156 kilograms meters per second. That's the total initial momentum. The final momentum, though, which has to equal the initial momentum, and I've got a vector symbol over it, and that's just indicated by the positive direction. It's one-dimensional motion, so the fact that they're positive is giving it the magnitude, the direction. So in this case, we're going to get a 3.00 kilogram plus a 100 kilogram mass times V M plus SB. So if we set that equal to 156 kilograms meters per second, we're going to get V me plus board is going to be about 156 divided by 103. And that gives me 1.51 meter per second. So that's the velocity of me and the skimboard. Now, this is a classic Mr. Younger skimboarding case. So what has happened now is I threw the skimboard at 2 meters per second. I didn't necessarily know that was the measurement, but our eyes are actually really good at detecting where something's going to be based on a few intervals at which we're watching the object move. So I have more than likely at that point set my body to lean the appropriate amount for moving at about 2.0 meters per second as I run up beside it and jump on it. However, because I won't quite matching the speed so much, I end up slowing the board down, and I'm leaning forward as if I'm ready to take off at 2 meters per second. So I end up falling face first on the sand, and that's what happens. If you do it the other way and you're actually running maybe 2.5 meters per second instead of 2 meters per second, and the skimboard's going 2 meters per second, what's going to happen then is you're still going to be slowed down, this time by the skimboard. It might not be so bad. You might fall backwards. So that's a typical conservation of momentum problem, not a hard one, mind you. Does anybody have any questions on that before I move on? You can also do the same thing with regards to recoil for a rifle. You can look, I have a recoil for like I think I did a recoil for AR-15 in one of my online videos on YouTube. Basically, if you know the muzzle velocity for a particular gun and you know the weight of a particular gun, and then you know the mass of the actual projectile of a particular gun, then the initial momentum of the gun bullet system is 0 because nothing's moving initially, right? But then after the trigger's pulled, it causes an explosion inside the shell. The shell pushes forward on the actual projectile. The projectile then sort of rifles down the barrel of the gun at a velocity of V bullet, right? Well, that means little m, the mass of the bullet, times big V, because that's the fast velocity, which is the muzzle velocity. That's the momentum of the bullet, and that's going to the right. However, the initial momentum was 0, so the momentum of the rifle has to cancel that out, which means you've got the the big M, which is the mass of the rifle, times the little v, which is the recoil of the actual rifle. That's going to turn out to be negative if you call the bullet going in the positive direction, but that's the actual recoil velocity of the rifle. If you're not wise enough to know how to shoot a rifle or a shotgun or something like that, and you do something crazy like maybe looking out the scope and just have your eye right in front of the scope, but without the butt of the actual rifle up against your shoulder, or if you're just holding it out in front of your shoulder without touching your shoulder, you're probably going to be caught off guard, because the velocity of that rifle, though it's quite a bit heavier than the bullet, is actually still going to be fairly large, and it's going to come back and give you a nice little bruise. So you can do that as well. That's another type of conservation of momentum problem. Very straightforward one, but you can see one on my YouTube channel if you'd like to do that. Now let's go on to a little bit more of the types of collisions we're going to deal with. So what I'm going to deal with now is imagining a one-dimensional elastic collision. And again, elastic means conservation of kinetic energy. And since it's a collision, we're going to assume that the net force is 0. Again, you're going to have weight acting on each of the objects rolling in one dimension, but they're going to be canceled out by the normal force. You're going to have friction forces that should be a lot smaller. But a good example of this would be pool balls, because pool balls are actually quite rigid. And rigid is what you want for conservation of kinetic energy. I mean, you can immediately tell it's not going to be conservation of kinetic energy, because you're going to hear sounds. The very creation of sounds means energy is being stolen from the system. So clearly it's not going to be perfectly kinetic or perfectly elastic, but it's going to be pretty close. So what we'll have in a one-dimensional elastic collision, we're going to have MA times VA plus MB times VB is equal to MA times VA prime plus MB times VB prime. That's going to be equation 1. And since it's elastic, I'm going to have equation 2, which is 1/2 MA VA squared plus 1/2 MB VB squared equals 1/2 MA VA prime squared plus 1/2 MB VB prime squared, right? Well, I'm going to try to group up the MA terms in equation 1. So from 1, I'm going to get a new equation. I'm going to say MA times VA minus VA prime is equal to MB times, in this case, it's going to be VB prime minus VB. That's going to be what I call equation 1 prime. I'm going to do a similar action with equation 2. And I'm going to go ahead and get rid of the 1/2. So I'm going to multiply through by 2 and don't have to worry about that anymore. I'm going to say MA times VA squared minus VA prime squared is equal to MB times VB prime squared minus VB squared. That's going to be called equation 2 prime. Okay. Now I'm going to write equation 2 prime like this, and I'm going to call it 2 double prime, and it's going to be MA VA plus VB, or excuse me, VA plus VA prime times VA minus VA prime is equal to MB times VB prime plus VB times VB prime minus VB. Everybody see the trick I did there from your old school algebra? The difference of squares is just a plus b times a minus b. So now I'm going to divide 2 double prime by 1 prime. And you see what's going to happen. I'm just going to be left with VA plus VA prime is equal to VB prime plus VB. I can play around with that a little bit and say VA minus VB is equal to negative VA prime minus VB prime. Okay, what that means is the relative velocities of the two things just reverse each other. So that's a very useful equation. That's one you can use. Your book calls it equation 9-8. Okay, so because of that, that's one you can actually use on your equation sheet for face-to-face tests and that sort of thing, but it is something valuable. So let's consider a special case where you're playing pool. And of course, with pool balls, the balls are all about the same weight. So MA is equal to MB is just going to be equal to plane M. And what I want to do is I'm going to say, consider billiard ball A of mass M moving with speed VA collides head on with ball B of equal mass. What are the speeds of the two balls after collision, assuming it is elastic? And assume A, both balls are moving initially, and B, ball B is initially at rest. So if I want to consider all the balls having the same mass, then I can do with this new example, pool balls, MA equals MB is equal to just plain M. So conservation of momentum, which was equation 1, is going to become, and actually I think I wonder if your book numbered that too. I'll double check real quick, see if your book numbered that. Yeah, it called that, using the wrong thing. It did not call that anything. Let's see if I checked it in the other. I think it did in the previous iteration. Yes, it did, 9-3. So this was equation 9-3. So that's another equation you can use. And then when it introduced conservation of kinetic energy, it called that 9-7. So those are all equations you can use. So from 1, I'm going to get VA plus VB is equal to VA prime plus VB prime. So that's just from 1 in doing this problem. Now I can also make use of equation 9-8, which I might also call equation 3, say. Okay, so now I can say VA minus VB minus VB is equal to negative VA prime minus VB prime. Okay, if I add those two, okay, I wrote that backwards as far as the bracket goes, but if I add those two, you can see the left-hand side gives me VA plus VA, but VB minus VB. And then the right-hand side, notice the VA prime is negative in the bottom equation and positive in the top, so that's going to disappear. But the VB prime is positive in the top and bottom, so I get 2VA equals 2VB, or VA equals VB prime. Okay, so when you take two pool balls and you hit ball A at ball B, and ball B happens to be moving already towards it, basically the final velocity of B will become the new velocity, or the initial velocity of A. Now, if we subtract those same two, whoa, Nelly. If we subtract Then we're going to get the left-hand side would be VA minus VA plus VB minus negative VB. So that's going to be 2 VB, which I'm going to write VB first because I suspect I'm going to get another 2 on the other side. And then I get VA minus negative VA prime, or it's VA prime minus negative VA prime. So that's going to be 2 VA prime. So I'll say that's VA prime. And then VB minus VB prime. So that's going to actually cancel out. So in fact, I do get VB is equal to VA prime. So what you see is the velocities just trade. So the cue ball comes in with a velocity of 3 meters per second, and the let's say the 2 ball, well, I shouldn't say 2, that rhymes with it. The 3 ball comes in with 3 meters per second. After the collision, the cue ball is now going to be moving at 3 meters per second, but the 3 ball is going to be moving at 2 meters per second. Okay, that's what we get for this type of problem. Any questions on that? This is for part A, where VB does not equal 0. Okay, so now if I want to do the same thing where VB is equal to 0, that means the cue ball hits a resting ball. 3 ball, say. So I now have VA is equal to VA prime plus VB prime, but I also have VA, that was supposed to be VA minus VB, but it's just 0 now, is equal to negative of VA prime minus VB prime. Okay. So if I add the 2 equations, let's see what happens. I get 2 VA is equal to VA prime minus VA prime plus VB prime minus negative VB prime equals 2 VB prime. So the answer is that VA is equal to VB prime. That's going to be one of my solutions. So in other words, the bullet or the cue ball is going to come in with a velocity of say 2 meters per second, and the 3 ball is going to be sitting still, and then all of a sudden the cue ball or the 3 ball is going to take off with exactly the same velocity that the cue ball had. Now let's do subtraction, which I think you can see VA minus VA is equal to 0. And when I do that, now I'm going to do VA prime minus negative VA prime gives me 2 VA prime. And then VB prime minus negative. So that gives me, in that case, what is it? VA minus, yes, yeah, that's 2 VA, right? And VB, this would be plus VB prime, but now I have to subtract it, so it's minus VB prime. So I just get 2 VA primes equal to 0, which means that VA prime is actually equal to 0. So in this case, I think you can tell this is the case where the cue ball comes to a stop. So this is like Newton's cradle. I'm sure you've seen Newton's cradle before, but you imagine a little bar like this, maybe like parallel bars, and you have a string attached to a ball, another string attached to an identical ball, another string attached to an identical ball. You can tell they're fairly elastic because of the way they behave. If I pull one ball out, it comes in, boom, and then one ball pops out. at the exact same speed the other one did, because it basically rises to about the same height as the other one did. Okay, so that's what we're seeing here is Newton's cradle in action. Any questions on that? So that's a nice, neat little problem to examine. So there's two scenarios when you're playing billiards. If you really are using fairly elastic collisions, either the two objects trade speeds. So you hit the cue ball, it hits the 3 ball, and that happened to be moving, by the way, which is not typical pool, but it did happen to be moving. And then they just trade speeds. The other scenario is a more realistic pool ball scenario. Is you hit a cue ball at 3 meters per second, it hits the 3 ball, and then the cue ball comes to a stop, and the 3 ball moves off of 3 meters per second. Okay. Now let's imagine another scenario. Let's imagine unequal masses. In an elastic collision. Okay. And the target's at rest. So with that case, I've got basically, let's say MA VA is equal to MA VA prime plus MB VB prime, which I can rewrite as MB VB prime is equal to, let's say MA times parentheses VA minus VA prime. Yeah, that works. Okay. So I can also use my other equation, which was equation 9-8, or equation that I called 3, which was VA minus VB is equal to the negative of VA prime minus VB prime. In this case, of course, we have VB equals 0. So that gives me VA is equal to VB prime minus VA prime. So with that in mind, I can now use what my VA prime is. So let's solve this equation for VA prime. VA prime, which is one of the things we don't know. That's why I'm trying to eliminate it. VA prime, I could pull it to the other side, and it would be VB prime minus VA. Let's call this equation 4, say, and I'm going to plug 4 into, let's plug 4 into what I called equation 5, even though I put it out of order. Okay. So if I do that, I can say into 5, I'm going to say now that MB VB prime is equal to MA times VA minus MA times VA prime, which is going to be VB prime minus VA. So getting that, I get MB VB prime is equal to MA VA minus MA VB prime plus MA VA prime. So it looks like now we can solve for VB prime in terms of VA. Oh, that's supposed to be just a plain VA over there, right? I already, yeah. Hold on a second. I just see just saw an error here. When I went to substitute VA equals, excuse me, when I went to substitute VA prime equals VB minus VA. I think I made a mistake. So let me erase this line right here and catch what I'm doing. Okay, so I'm plugging for, oops, that was not helpful at all. That was supposed to be VA, if I remember correctly, is equal to VB prime minus VA. Yeah, okay, that's the same thing there. So I'm going to plug that number 4 into 5, and that's going to give me MB VB prime is equal to MA VA minus MA times VA prime, but I said VA prime. Oh, maybe that's the problem. Yeah, this is supposed to be a prime there. Okay, so I'm substituting that VA prime in here. So this should be MA VB prime, and then minus MA times minus VA. That'd be plus MA VA. So this gives me, notice I can get 2 MA VA. That takes care of this term and this term. And I get equals, pulling the VBs over there, I get MA plus MB times VB prime. So now I can actually solve for VB prime, and I see that VB prime is equal to, check this out, it looks like the tension formula from the Atwood machine. Now this is a big deal. Not to make it too macabre of a point, but when small cars get hit by big cars, this is a horrible result. But if you have, for instance, well, let's take let's take one of my favorite songs right now. My money don't jiggle jiggle, it folds, right? So you take your little Fiat and you're sitting at a stoplight, and then you see a big Mack truck come in. Sadly, you know, Mack truck drivers generally are professional drivers, and they actually drive quite well. But if one kind of had a brain fart, maybe either had a heart attack or was actually texting, that would be bad. The Mack truck might come in at 60 miles per hour and hit the said Fiat. If that's the case, then MA is much larger than MB. So that denominator, MA plus MB, is essentially just MA. You see then that you've got 2 MA over MA times VA, which means that the little Fiat is going to fly off not at 60 miles per hour like the Mack truck had, but at 120 miles per hour. So that's exactly why it's so much more dangerous to be hit by a bigger car if you're in a smaller car. So that's obviously a good reason for us to, you know, everybody buy SUVs or tanks or something like that. There's reasons for not doing that, of course, but in a collision, a motorcycle always loses, and smaller cars loses to big cars, and that's one of the reasons. Okay, now you can play around with the math a little bit more. Actually, we got plenty of time, so we've now got an expression for VB prime. Now what we want to do is get an expression for VA prime, and all we have to do with this is we can substitute this value of VB prime back in to the equation. VA prime is equal to VB prime minus A. So I'm going to do that now. I swear I'm going to do that now. So I had the equation VA prime is equal to VB prime minus VA. And I had the expression that VB prime is equal to 2MA over MA plus MB times VA. So I can actually plug this. Whoa, why does it keep switching to it? That is not helping me at all. Okay, so I can plug that back in to the VB prime expression and solve for VA prime. So the VB prime in this case is actually equal to VA prime minus or plus VA. So I can say VA prime plus VA is equal to 2MA over MA plus MB times VA. Obviously, you can see a common term of VA over there. I want to get a common denominator, so I'm going to say VA prime is equal to MA plus MB over MA plus MB. But by moving it over there, technically, that made it a negative times VA. And that's going to be added to 2MA over MA plus MB. Whoa. Times VA. So I see I have a common term of VA. That's wonderful. But what I'm going to say now is VA prime is equal to 2 times MA minus MA minus MB. In other words, I made one big numerator out of all that crap. All of that over one big common denominator, MB. And all that times VA. So finally, I get VA prime is equal to 2MA minus MA is just MA. And then minus MB over MA plus MB. All that times VA. So remember with the Atwood machine, we got A was equal to M2 minus M1 over M2 plus M1 times G was the acceleration. And we got T is equal to 2M1 over M1 plus M2 times M2G, right? Notice here we got VB prime is equal to 2MA over MA plus MB times VA. So that's what I'm talking about. It sort of looks like the same formulas, okay? Now, in this case, you can also say, well, what if we already handled the case MA much greater than MB implied implied VB prime was approximately equal to twice VA. But what if we had MB is much greater than MA? Okay, if MB is much greater than MA, then what you're going to get is VA prime is just going to be equal to the negative of VA. I think I might have said M there, but I didn't mean it. Because you see what happens there is the MB is really huge compared to the MA. So MB plus MA is essentially MB, and MA minus MB is essentially negative MB. So what happens is, and I can attest to this because though I'm a big guy, I'm not football big, and I was running across the track at NC State. And I was looking across at the other side of the track at a person that had no legs and was running really, really fast. He had like those prosthetics that sort of look like they bend backwards, like cricket legs or something. And he was flying. I was like, man, that dude is fast. And I was just looking at him, and I heard a woof, 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 woof. And I looked to my right. About that time, I saw it was an inside linebacker for NC State's football team, a very, very large dude, like 6'5", probably well over 300 pounds. And I'm thinking, oh man, I really screwed up. I could hurt this guy. I feel bad. So I hugged him and caressed him as he hits me. And in fact, I got knocked away at basically a really high speed. And I was just sort of holding on to him like I'm some little, baby koala on a koala bear. And he said, oh man, you're all right. I said, yeah, are you all right? I'm so sorry. He said, "Yeah, I'm fine, man. Are you okay?" I said, "Yeah, I'm good." And I walked off and started urinating blood. I bruised my kidney and that sort of thing. So that's a very real thing. If something much, much bigger than you runs into you, or you run into it, you're pretty much going to bounce off of it with the exact same speed you came in with. That's also another trick from Magic Begins with an M, or excuse me, I think it's called Physics Begins with an M, Magic, Myth, and Mystery. And they give you an idea where you're riding down a 1-lane road and all of a sudden you see that a car identical to you is going probably the same speed you are, but in the opposite direction. Say you're going 60. You're driving a Volkswagen Beetle, they're going 60, they're driving a Volkswagen Beetle, and your choice is to either run head on into them or to run into a ginormous immovable tree. Which choice do you make? The trick is that there really isn't a good answer because both of them are going to be the exact same result. As you can see here, if the thing is immovable, which is what happens when MB is much, much, much greater than MA, then you're going to bounce off that tree with the negative of the velocity that you had. So you're going to go from 60 to negative 60, which is a horrible thing. If, however, you actually run into an identical car, the same one, more or less the same thing's going to happen. So that's another physical principle. Now let's look what happens to the velocity v prime. So in that case, vb prime, where mb is much, much, much greater than ma, is essentially going to be just plain. Notice the mb is much, much bigger than ma. So what's going to happen is I'm going to have essentially v prime is equal to 0. Because I'm sort of, you can imagine taking the limit as MB approaches infinity, then 2MA over MA plus MB just becomes basically 0 times VA. Okay. Any questions on that? So these are expressions you can use, and your book is even cool enough to give you a more general expression. I'll write it down here. Let me see if I can find it real quick. Your book gives you an actual more general expression, and that is this. And it tells you can see problem 40 to solve it for yourself. But if you're not taking into consideration the initial velocity being 0, everything I just drew there was horrible. If you're not taking into consideration VB having an initial velocity of 0, then VA prime, the final velocity, would be VA times MA minus MB over MA plus MB plus VB times 2MB over MA plus MB. Notice they did not number that equation. Additionally, VB prime is equal to VA times, in this case, 2MA over MA plus MB plus VB times, guess what? MB minus MA. So those are two expressions you can use when you're solving problems. But notice it says do not take time to memorize them. You should, usually a lot of cancellations will pan out in such a way that it's more efficient to just solve them in real time. But that is an actual solution for the one-dimensional collision problem. I can show you another one, which is kind of neat. And this is a, let's say, a two-dimensional elastic collision. With VB equal to 0. Okay. So, and we're going to say pull balls as well. / identical balls. Because momentum gives you this. You get VA is equal to VA prime plus VB prime. So what we see is VA prime plus VB prime adds to give you VA. Okay. That's an actual solution of the two-dimensional identical ball collision problem where the B ball is sitting still. However, if it's also elastic, remember you can get rid of the 1/2 and the M's by being elastic. So in that case, you're going to get VA squared is equal to VA prime squared plus VB prime squared. Well, that's only true with that diagram in very certain cases. Can anybody tell me when the second blue equation is true given the blue diagram?
We're talking about like if it's a right triangle.
Exactly. That's one of the results. So one result is that I don't know what these, oh, I hit my keyboard. I ain't just being a jerk. Okay. And then what do you do that for? Okay, that was crappy. Just when I think I'm getting used to the stupid program, I find out I am not getting used to the stupid program. Okay, so in this case, this is VA, the initial velocity of the A object. And then the final velocity of the A object. And the final velocity of the B object make 90 degrees with each other. So that's one solution. Another solution VA is equal to VA prime and VB prime equals 0. That means you missed. But notice that's completely consistent with the equations, right? And then the other one is third result. Is VA is equal to VB prime and VA prime is equal to 0, which is basically the same expression we got earlier for two head-on cue balls where the cue ball hit the ball sitting still. So this is trade velocities. Okay, so that's your three scenarios that can occur in 2D with an elastic collision. They can completely miss each other, in which case VA runs off with, at the same velocity that it had before the collision because it completely missed. VA completely loses all its velocity, but VB gets exactly the same velocity and moves off in the same direction. Or finally, the two have to make an angle, and that literally means like VA is here, VA prime is here, and VB prime is here, and that makes a 90-degree angle. Now you can test that a little bit in pool, and you'll see that the more spin and stuff like that you put on the actual cue ball, the smaller or bigger this angle will get from 90 degrees. So that's kind of neat. But anyways, that's wrap up, if you will, of the two-dimensional elastic collisions where one object sits still. So does anybody have any questions on that? As I told you, perfectly inelastic collisions are when objects run into each other and stick together. I'm going to show you an example of that called the ballistic pendulum. So let's do that real quick, since it seems like no one has any questions. So let's say ballistic pendulum. So what you can imagine doing is you can take a huge massive block of mass big M, and you can fire into it a little massive bullet of velocity big V. Okay. And you know energy is not going to be conserved in this scenario because you're literally going to heat up the block, matter is going to be torn out of the way, all sorts of crazy stuff. But what's going to happen is that massive block is going to have a hole in it like that. That was not the drawing I thought I was going to make. And I don't know how to fix it now, but we'll go with it and pretend we're not in third grade. Okay. And then what's going to happen is right here, momentum was conserved. From here to here, momentum was conserved. But then what happens, actually, is the mass here. Notice this mass is M plus little m. This mass is also M plus little m. All mangled up inside there. Okay. But in fact, the object has risen in height h. So what we had was P initial equals P final. That gave us little m big V is equal to big M plus little m times V initial. Okay. So that V initial is that velocity right there. Okay. We can solve for that V initial. In fact, V initial is going to be equal to M over big M plus little m times big V. And big V, I'm just specifying that because that's like the muzzle velocity of a bullet or something like that, right? Now we're going to use work in plus U initial plus kinetic energy initial equals work out plus U final plus kinetic energy final plus E loss. We're only taking it from the instant the bullet is embedded in the block, i.e. the blue picture, up till the block reaches its max height. So work in is 0, work out is 0, E loss is 0, potential energy initial is 0, and kinetic energy final is 0. So what we're going to get is 1/2 of M plus big M. That's the total mass of the block when it takes off with velocity VI, which by the way is M over M plus little m times big V squared. That's got to equal big M plus little m times G times H. Okay. So from that, you can actually solve for, let's say, V, which is normally what you do. You could fire this bullet into a ballistic pendulum and use that to determine the muzzle velocity of the bullet. What I'm going to do here is I realize I got a common factor of M plus M. I'm going to divide that out. Then I'm going to multiply through by 2. So I'm going to get M over M plus M times, and that's squared, times V squared is equal to 2GH. So that's going to give me V, the muzzle velocity, is equal to the square root of 2GH times, in this case, M plus M quantity squared under the square root divided by little m squared, or finally you can say the muzzle velocity has got to equal the square root of 2GH times M plus M over M. And that again is another nice way of writing it. In physics, we like to write a quantity that has the units you want. That's the square root of 2GH. You know from V squared equals V0 squared is equal to 2GX. You know that has velocity units. And then times some number with no units. Well, M plus M over M has no units. So that's a typical ballistic pendulum problem. Anybody have any questions on that one? Now, I worked all that with just symbols. Your book has an example like it with other than symbols. Your book also works out in section 9.7 collisions in 2 and 3 dimensions. I don't think that's really that hard. I've shown you sort of all the real algebra tricks that have to happen. And I think if you can do example 9.12, so I'm going to write it this way: make sure you can do example 9-12, and that's page 228. If you do that, you're probably in a pretty good spot, because it's really hard to make two-dimensional collision problems, whether they be elastic or not, such that you don't over-determine it or under-determine it. So really, when we go to make up physics problems, we look for ones that have already been made up and try to use those. So your book actually solves on page in 227. It shows you a way of going through and computing collisions, momentum being conserved in collisions, and it not even taking into account elasticity of the collision, and just assuming that it's not elastic. And then it solves the problem where basically a ball A runs into a stationary ball B, and then ball A and B leave off at different angles. In this case, they give you that the two angles are 45 and negative 45 degrees. The initial velocity of VA is 3 meters per second. And then they're just trying to get you to calculate what is VA prime and VB prime. So you can always set up your coordinate system if you have. Let me stop sharing for a second. Or actually, let me stop sharing permanently for that matter. Where are you? So you can always have, for instance, a projectile coming in like this at this velocity, hitting a stationary object, and then the stationary object shoots off this way and the other object shoots off this way. That can be done, but that's a really bad coordinate system if you just say, X is to the right and Y is vertical. What you'd want to do is tilt your axes so that at least that initial velocity has only one component. So that's the first thing you want to think about, is twist your coordinates if they ever give you some weird problem like that. An incoming projectile has a velocity of 30 meters per second at an angle of 30 degrees below horizontal. No, you're not going to do that at all. You're going to say the positive x-axis is at an angle of 30 degrees below horizontal, and the positive y-axis is, of course, 90 degrees above that. And then by default, you have no momentum component in the vertical direction. So your initial momentum in the y direction is 0, and your final momentum in the y direction is going to be MA VA prime cosine theta and MB VB prime cosine theta, stuff like that. Or excuse me, sine theta in both of those cases. And then the X components are actually going to have something other than 0. It's just going to be VA is equal to MA VA cosine theta plus MB VA prime or VB prime cosine theta. So, and you can see how that works, but just make sure you look for the simple cases. You always want to choose your coordinate system to make the problem as simple as possible. So if you have a bunch of forces that are all acting at 45-degree angles, just consider twisting your whole coordinate system by a 45-degree angle, and then none of them will have anything but X and Y components. In the case of a collision, make sure your initial, if you only have one object moving, make sure that object only has one component. Put your x-axis parallel to that, and then you'll have initial momentum in the y direction being 0. So I think that's enough. I'm looking at what people, yeah, it looks like y'all have answered everything amongst yourselves. Good job. So we've got to 7:36. Y'all got another 14 minutes technically left for the class. I am going to go ahead and call it. We've done chapter 9 ad nauseum. The only thing we didn't cover was center of mass. I could do a bang up job really quickly on that. I don't think that would do you very much good, but I think watching my YouTube videos on center of mass would be better. I will tell you this though, if you imagine this as being a rod and maybe we have a fulcrum somewhere over here, you could find somewhere over here where you could hang, say, a 3-kilogram mass, and that would balance the actual pin. Okay, or maybe it's got to be smaller than a 3-kilogram mass, but the main thing is some mass at some distance away. Since the pin's horizontal, that force would actually be acting perpendicular to what we call the lever arm, and it would tend to rotate it this way, whereas the center of mass of the pin is right about here, so it tends to rotate about the fulcrum this way. Those two competing torques is what they're called, are really proportional to the mass times the distance away from the rotational point. When you actually put a weight on this side that keeps it from rotating, what you've done is you force the center of mass of the system, which includes this mass, this pin, its center of mass, and this fulcrum, applying a force for upward. You've created the center of mass to be right over the fulcrum. And that center of mass, from thinking about those torques, must be related to the product of the mass times the distance away. And in fact, the center of mass in the x direction is m1 x1 plus m2 x2 plus m3 x3. And it doesn't matter where you use the coordinate origin, you just have to choose one. And then you take each individual distinct mass and multiply it by its distance away from the origin, whether it be negative or positive. You're actually using its coordinate, not its distance. And you add all those m times x's up, and then divide it by the total m1 plus m2 plus m3, however many masses, and you get the x center of mass. It's where along this you can stick your finger under, because that's what the center of mass is. It's the point where the object acts like all of its mass is located. So if I, for instance, threw a baseball bat like this, okay, y'all know a baseball bat is really, it's got a bubble on one end, it's got a thin handle, and then it's got a fat tube on the end. So the center of mass of that thing is where you could put your finger under it and balance it, not vertically, but horizontally. You would see that that has to be closer to the fat end. So the center of mass of a baseball bat is a little closer to the fat end than it would be to the skinny end. So if I took and threw a baseball bat, the only thing that would exhibit that projectile motion of a hyperbola, like we learned about, is the center of mass. What you'd see is the bat swinging like this, spinning, 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 and then you'd see this one little spot making a perfect parabola. That spot is the center of mass, okay? And the way you calculate it is you take the product of the masses times their x coordinate and divide it by, add all those up, and then divide it by the sum of the individual masses. Same thing with the y, you take the m1 y1 plus m2 y2 plus dot, 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 and divide it by the sum of the masses. Well, in the case of a baseball bat, that's not made of little slices. I mean, you could cut it up into little slices and do it that way if you wanted to, but your bat would be kind of crappy from there on out. So what we do is we imaginarily slice it up into little pieces called Riemann sum. And then it becomes the integral of x dm over the integral of just dm, where dm is the differential mass element. Dm is usually like a lambda times dl, where lambda is the mass per unit length. So you can literally, if it's uniformly distributed, take the total mass divided by the total length, that's lambda. Or it could be a sigma dA, where dA is a differential area element, and sigma, if it's uniformly distributed, is just the total mass divided by the area. Or it could be a rho, which is that P looking thing, times a dV. In that case, the rho could be, if it's uniformly distributed, the total mass divided by the total volume. So you'll see I did a couple of centers of mass with integrals. I did a couple of centers of mass with a train car. That one's pretty cool. And I did a conservation of momentum problem with the same train car, and was able to show basically, but through that you can either use center of mass considerations or conservation of momentum considerations to solve the same problem. So that's why they actually introduced center of mass in this chapter, is because it is closely related to conservation of momentum. And that's also why I talked about the center of mass frame when we talked about inelastic collisions. So we're done. If anybody has any questions, I will wait for the last person to leave. Other than that, you guys are free to go. I hope you have a nice weekend. Remember, Monday we have off. And your homeworks, I think I've made them all due on the 5th as opposed to the 3rd. And chapter 10 should not be due until I believe it's the 10th.
Thank you. Have a happy 4th, Professor.
You too, and thank y'all for coming.
Thank you.
Professor,
Yes.
would you be able to go back to the page where you said a cue ball hits a resting 3 ball?
Yes. Let me get there. Now I'm putting this down here, mirroring my screen here. Okay, so this is roughly where I started talking about it. Actually, I talked about it before on the previous page. Is it this page that you want or the other one?
It was the one with the Newton's cradle.
Okay, gotcha.
I was confused as to what the symbols. Oh, those are the balls swinging in either direction.
Exactly.
Okay.
Yeah.
And then to the right of target where it says like 0-0, is it 0- or equals or arrow, or what is that?
To the right of the target.
Where it says unequal masses, comma, elastic collision.
Oh, gotcha. Yeah, so unequal masses, elastic collision, but the target has a velocity v equals 0.
Oh, okay.
So that means one of them sitting still.
All right. Those were my questions.
Okay, I'm going to be posting this to my Google Docs page in about 2 minutes, so you can also download it there if you'd like.
All right, thank you.
Notice the
Have a good
file
one.
name. Oh, actually, you can't. It's PHY241_N01C. That's just your course number and section number, but there's an underscore between the 241 and the N01C, and then between the N01C and today's date, which is 06/29/22. Okay.
All right, thanks. Have a great day.
You too. Have a good one. Looks like everybody's gone. Y'all have a good one.